For 4 decades, India has poured resources into a singular aerospace ambition, engineering an indigenous fighter jet engine from scratch. The result of that effort is the DRDO GTX 35VS Cavari. The Cavari was originally designed for one specific airframe. It was meant to power the Tejas light combat aircraft, aiming to sever India's reliance on foreign propulsion suppliers like General Electric. But in 2008, the Indian government officially severed the Cavari from the Tejas program. The engine could not meet the strict performance metrics required for supersonic combat. To the global aerospace community, this public delinking branded the project as a high-profile, multi-million-dollar failure. Yet today, a direct derivative of this exact engine is currently airborne, undergoing final in-flight testing mounted to an Il-76 transport aircraft in Russia. Its new destination is the Katak, India's classified 13-ton stealth unmanned combat aerial vehicle. The engine is on track to achieve full certification by 2026, which will unlock the Cabinet Committee on Security's approval for full-scale manufacturing. The severe thermal constraints and weight penalties that disqualified the Cavari from powering a manned supersonic fighter are exactly what makes its non-afterburning variant the optimal propulsion system for a deep-penetration stealth drone. To understand why the Cavari was rejected, we must look at the raw physics required to fly the Tejas. The aircraft needed a low-bypass turbofan capable of pushing 81 to 85 kilonewtons of thrust while engaging an afterburner. During testing, the Cavari's thrust peaked between 70 and 75 kilonewtons. It fell critically short of the minimum power required to execute combat maneuvers. This cross-section isolates the engine's kabini core, the high-pressure compressor, combuster, and turbine, where the bottleneck occurred. Here, turbine blades spin at over 10,000 RPM. Simultaneously, operating temperatures easily exceed the natural melting point of their construction metals. Advanced aerospace nations solve this by forging single-crystal turbine blades from highly specialized superalloys designed to withstand extreme thermal loads. During the Cavari's initial development, India's domestic industry lacked the manufacturing infrastructure required to produce these single-crystal materials. As a direct result, the engine suffered recurring failures in the high-pressure turbine section during mandatory extended endurance test runs. The standard alloys were subjected to thermal fatigue. Extreme heat and immense centrifugal stress caused the metal to develop microfractures and degrade rapidly. To compensate for the material weakness and prevent the blades from shattering, engineers reinforced the components, designing them to be physically thicker and more robust. This overengineering triggered a cascading problem. The additional metal caused the Cavari to become drastically heavier than its specified limit, ballooning past 1,400 kilograms in early prototypes. For a light fighter, any excess engine mass destroys the aircraft's thrust-to-weight ratio. The added bulk severely restricts the plane's agility, fuel capacity, and payload limits. The inability to mass-produce single-crystal metallurgy trapped the Cavari below its required thrust threshold and finalized its rejection from the Tejas fighter program. The operational envelope of the Katak UCAV, however, requires an entirely different propulsion profile. The Katak is a 13-ton flying wing drone designed to execute deep penetration strikes at high subsonic speeds. Fighter jets require an afterburner, a component that injects raw fuel directly into the exhaust stream to generate massive bursts of supersonic speed. For a stealth platform, an afterburner is a severe tactical liability. It consumes fuel rapidly while generating immense noise and extreme thermal output. This thermal data shows the difference. An afterburner's massive bloom makes aircraft instantly visible to heat-seeking sensors, while the drone maintains a constrained exhaust profile. Recognizing this, DRDO physically stripped the afterburner off the original Cavari, creating the dry Cavari, or KDE. The Katak drone requires only 46 to 52 kilonewtons of continuous dry thrust. This operates well below the Cavari's previous 75 kilonewton failure point. Throttling down the engine's maximum output entirely transforms the thermodynamic environment inside the kabini core. The lower combustion temperatures mean the standard, heavier turbine alloys are no longer subjected to the extreme thermal fatigue that caused them to fail. Eliminating the bulky afterburner section also provides an immediate and massive reduction in the engine's overall mass. Engineers are currently refining the remaining materials to drop the dry Cavari's total weight below an ideal target of 1,000 kilograms. The dry variant has already passed its ground trials and is executing the final stages of high-altitude evaluation. The engine is now remarkably close to operational readiness, requiring just a few dozen more hours in the air to cross the critical 100-hour flight validation milestone. By stripping away the extreme performance demands of manned supersonic flight, the exact same engine core transitions from a metallurgical liability into a highly reliable, low-signature power plant engineered for stealth. For years, defense analysts have criticized the 4-decade, $239 million Cavari program as an absolute waste of state resources. To evaluate that claim accurately, we must use technology readiness levels, or TRL, the strict scale used to measure the maturity of new hardware. Before the Cavari project began, India's domestic capability to design and build aero engines sat at a nascent TRL 2 to 3. This diagram maps out the resulting technical ecosystem. Despite missing the Tejas integration, the successful development of the kabini core elevated India's manufacturing base to a robust TRL 6. From that proven core, the technology tree splits. The Cavari derivative engine powering the Katak shares a massive 75% parts commonality with the original fighter engine. The engineering also branched horizontally. The Cavari marine gas turbine was spun out to provide 12 megawatts of shaft power for naval warships. Beyond the engines themselves, the project forced India to build the invisible, foundational infrastructure required for aerospace development, establishing high-altitude testing facilities, writing full-authority digital engine controllers, and certifying domestic aerospace alloys. A nation cannot skip straight to building fifth-generation fighter engines. Mastering these foundational elements is the strict, unavoidable prerequisite. Evaluating the Cavari solely as a failed fighter engine misses the actual scope of the engineering. It was the necessary capital expenditure to build a sovereign propulsion ecosystem, one that is now mature enough to drive India's autonomous and naval fleets.